So now we're going to discuss trees. So let's start with a few definitions. A graph is circuit free if and only if it has no circuits. And remember that we defined circuits in the last section we talked about. And then a graph is called a tree if and only if it is circuit free and connected. So in order to have a tree, you have to have a graph that is both circuit free and connected. So let's look at a few examples. The following graphs are trees. So the graphs that'll look like this. And I'm not going to label any of the vertices and edges. That graph is connected and it contains no circuits. Also, just a single point, that graph would be a tree. It doesn't have any circuits and it's connected. And then finally, this graph, again, is connected and has no circuits. So all three of these are trees. And we will say, let me give you some examples that are not trees. The following graphs are not trees. So this graph is not a tree because it contains a circuit. And then this graph right here is not a tree because it's not connected. It has two different connected components. So now let's look at an example of a decision tree. So I'm going to give you this setup. This decision tree is used to determine students' placements. So they take a test and their score on part 1 of this test. So it depends on their score. If their score is greater than 10, if it's 8, 9, or 10, or if it's less than 8. Then there was a second part on the test, score on part 2 was greater than 10. They should be placed in Math 120. Less than or equal to 10 gets placed in a Math 110. Score on part 2. If their score was greater than 6, they get placed in Math 110. If their score was less than or equal to 6, they get placed in Math 100. And down here, it didn't matter what they scored on part 2. They get placed in Math 100. And so I want to know, based on this decision tree, what course should be recommended for a student who scored 9 on part 1 and 7 on part 2. So you're going to start at the beginning, right here, and you're going to break off depending on their score. So if you look, they scored a 9 on part 1, which means we should take this middle track here to this box, and now they scored a 7 on part 2. A 7 is bigger than 6, so we should take this path down to the final end, and the course that should be recommended for them would be Math 110. All right, so let's define a few more terms. Let T be a tree if T has at least 2 vertices, then a vertex of degree 1 in T is called a leaf. And sometimes instead of leaf, you'll see the phrase terminal vertex. Either one of those could be used. So if you have a degree 1 vertex in a tree, it's called a leaf or a terminal vertex, and a vertex of degree greater than 1 in a tree is called an internal vertex, or sometimes people would say, or a branch vertex. So again, a degree 1 vertex in a tree is called a leaf or a terminal vertex. If it has greater than degree 1, it would be an internal vertex or a branch vertex. So the last thing I want to mention about trees is the following theorem, which says, it's theorem 10.4.2 in your textbook, for any positive integer n, any tree with n vertices has n minus 1 edges. So let's look at this problem. I want to ask this question. A graph G has 10 vertices and 12 edges. Is it a tree? To answer this question, all we need to do is look back at this theorem. According to this theorem, if my graph has 10 vertices, how many edges does it contain? 1 less, so it has 9 edges, which means this is not going to be a tree. So the answer is no by this theorem, theorem 10.4.2. Any tree with 10 vertices has 9 edges, not 12.